Is the slide visible?
Yes, ma'am.
Okay, so please keep a page or a book and a pen with you. We just need to make some, you just need to note down few equations which are important. All the problems that we are going to solve here in this unit in the manual assembly line part, specifically when it comes to the line balancing problem, you will proceed the problem only after you solve all of these equations. So the very first step to solve all the problems is going to be these equations that we are going to write down, and then we will be using one of those different methods that we have, like the largest candidate rule or the Kilbridge investor method. One of those methods will be used and the problem will be solved completely. So let's start with analysis of single model assembly line. So here basically the relationships that are developed here, whatever relationships or whatever equations that we are going to see here are basically applicable to a single model assembly line. With some little modifications, the same relationships they can be applied to batch model lines. We consider mixed model assembly line in some other section. It's not in this particular section that we are discussing now. Okay, so just understand one thing, that these equations that we are writing, they are with respect to the single model assembly line mainly. With some modifications, they can be applied to batch model, the batch model assembly lines as well. Okay, and for the mixed model, we have different set of equations. Okay, so to start with, the assembly line, it must be designed to achieve a production rate RP which is sufficient to satisfy demands for the product. The product demand is often expressed as an annual quantity, which can be reduced to an hourly rate. So we know what is this production rate. We know we express the production rate in hourly rate. We usually use this constant 60 in order to convert whatever is the time frame given to hourly rate, right? So production rate we are already aware of. So the equation for production rate here is given by dA upon 50 into SW into HSH. So we know what is SW, we know it is shifts per week. We know what is HSH, it is the hours per shift. Why is this number 50 used here? So this 50, what is used here, it will change. Okay, it all depends upon the management. The management has to decide as to number of shifts per week for which the line is going to operate, and number of hours per shift. So suppose if you assume that the plant is going to operate for 50 weeks per year, then the required hourly rate is going to be given by RP is equals to dA upon 50 into SW into HSH. Suppose if they say that the assembly line has to operate for 100 weeks per year, then instead of 50 we will be using the number 100. So the denominator, basically the number that you see here, it depends upon the decision of the management as to how many number of hours um, you're going to function, or that particular assembly line is going to work. So here we know that RP is the average hourly production rate. The unit is units per hour. What is DA? DA is, that is D subscript A. It is the annual demand for the single product to be made on the line. Okay, and the unit is units per year. SW, we know it is number of shifts per week. HSH, it is hours per shift. So if the line operates 52 weeks rather than 50, then RP will be what? It is dA upon 52 into SW into HSH. So if a time period other than a year is used for the product demand, then the equation can be adjusted by using consistent time units in the numerator and the denominator. So please note down this equation correctly. This is equation number 1 in unit 3. That is, sorry, this will be equation number 3 actually, if you consider from the Manning level equations that you all have written. Or else you can just keep that aside, and with respect to assembly of single model assembly line, this will be the equation 1. RP is given by dA upon 50. The number 50 will change depending upon the number of weeks it operates in a year. that assembly line operates in a year, that into SW into HSH. So this production rate, that is RP, it must be converted to cycle time TC, which is the time interval at which the line will be operated. So the cycle time, it must take into account the reality that some production time will be lost due to occasional equipment failures, maybe some power cuts that are there, lack of certain components needed in assembly, maybe there's some quality problem, labor problem, or maybe there is some any other reason, XYZ reason. So as a consequence of all these losses, if you consider the time that is lost because of all these failures that for, because of these various reasons, which can lead to some or the other failure, the line will be up and operating only a certain proportion of time out of the total shift time that is available. So this uptime operation is referred to as line efficiency. So we basically have already, okay. So before that, we have the cycle time. It can be determined by TC. Just write down this equation. Cycle time is given by 60 into E upon RP. So we know what is E. It is line efficiency, and RP is the production rate. TC is the cycle time. Completed? Have you all written down the equations? So in this equation, we know cycle time, it is 60 into A upon RP, where RP we have already defined what it is. And I was just talking about what is this efficiency. So as I said, whenever it comes to um, the considering this cycle time, you have to think about the actual reality and how this actual production time can be lost due to these different types of failures. Maybe there are various reasons for these failures to occur, like some equipment failure or some quality problems, labor problem, all of these things if you consider, then the actual uptime proportion or the time for which the line is actually performing, that is referred to as the line efficiency. So the cycle time, it is determined here, it is shown, where we have PC cycle time in minutes per cycle, RP is the production rate, units per hour. If it is not in units per hour, then you can use this constant 60 to convert it from whatever unit to hours, that is minutes to hours, sorry, and E is the line efficiency. So basically, the typical value of E for a manual assembly line are in the range of 0.90 to 0.98. So the cycle time TC establishes the ideal cycle rate for the line. So we know what is this ideal cycle rate also. It is given by RC, that is 60 divided by TC. Ideal is something that is expected, and the production rate, when you see, that is something that is with respect to the reality, considering all the practical problems, success rate, everything considering, you get RP. And what is actually expected, the ideal cycle rate is given by RC, that is 60 divided by TC. So where RC is cycle time for the line, this rate RC, it must be greater than the required production rate RP. Obviously, it will be greater than the required production rate RP because RC is what is expected and RP is considering all the facts, because basically the line efficiency is less than 100. So line efficiency, basically it is defined as E is equals to RP divided by RC. So if you just rearrange all these equations as to what is RP and RC, you get the final equation for E as TC by TP. We know what is RP, we know the equation for RP, we know the equation for RC. If you just substitute those equations here, you finally get TC by TP. So efficiency, line efficiency is given by that equation that is shown here, TC by TP. So where basically TP, it is average production cycle. So we already know this is cycle time TC, and TP is what? Average production cycle time. Um, So what happens is an assembled product, it basically requires a certain total amount of time to build. So that time is nothing but the work content time. That is T subscript WC. So I'll repeat again, an assembled product, it basically requires a certain total amount of time to build. So the total time that is required to assemble a particular product, that is called as the work content time. So this is the total time of all the work elements that must be performed on the line to make one unit of the product. So the total time that is required from the start till the end, that is start of the assembly operation till the end, till you get the completely assembled part or the product, that is called as the work content. So it represents the total amount of work that is to be accomplished on the product by the assembly line. So it is useful to compute theoretical minimum number of workers that will be required on the assembly line to produce a product with known TWC and specified production rate. So it becomes very important with respect to these manual assembly lines. When it comes to these manual assembly lines, you have to find out what is the number of workers, minimum number of workers that are required on that assembly line. So in order to calculate that, knowing what is the total work content time and what is the rate of production is important. So the approach is basically here is to compute the number of workstations which are required in order to achieve a specified production workload. So we have this equation for the same. So the number of workers on the production line, that is W, it is given by WL upon A into E, where W is number of workers on the line, WL is the workload that has to be accomplished in a given period of time, and AT is the available time in that particular period. So this time of interest is usually 60 minutes. You can just write down this equation, how to find the number of workers on the production line. So here WL, that is workload. What is that workload? It is that period in the hourly production rate which is multiplied by work content time of the product. That is given by RP into TWC. So workload, it is calculated with the help of production rate into the work content time. Where RP is production rate and TWC is work content time. Please note down the units correctly. Okay, am I audible to you all? Are you noting it down?
Yes, ma'am.
So the above equation that is there, it can be rearranged to the form that RP is equals to 60 into E into TC. If you already know what is okay, we know this equation for TC. If you consider the second equation that you'll have written down, TC is equals to 60 into E upon RP. Right, if you rearrange that equation, you can write it as RP is equals to 60 into E divided by TC. Consider, just look into the second equation in the analysis part. You have written the equation for TC is equals to 60 into E upon RP. Just rearrange that. You get this RP is equals to 60 into efficiency, that is line efficiency, upon cycle time TC. So if you substitute the value of RP in this equation WL, that is workload, you get this new equation, that is 60 into E into TWC upon TC. So workload can be calculated also with the help of this equation. So the available time 80, that is 1 hour 60 minutes. It is multiplied by the proportion uptime on the line. So 80 is given by 60 into E, that is line efficiency. So you can see this equation W is equals to workload upon AT. That is number of workers on the production line is equals to workload upon the available time. If you substitute the terms workload with this new equation 60 into E into TC upon TWC upon TC and the available time is 60 into E, when you substitute it here, you get a new equation to find what is the total number of workers on the production line. So please substitute and tell me what is the equation that you get. So basically the equation, when you rearrange, it will reduce to a ratio of TW by TC, right? So you will be getting W, that is number of workers on the production line will be given by this equation TW into TC. So since the number of workers must be an integer, so we can state W star, it is equal to minimum integer which should be greater than or equal to TW by TC, the ratio of TW by TC. It has to be an integer. So when it comes to rounding off the decimal points that you get, you will be taking it to the higher level or the next number, where W star, it is theoretical minimum number of workers. So please note down this thing correctly, because sometimes they will ask you to find what is the theoretical minimum number of workers, not just the number of workers, right? So theoretical minimum number of workers and the equation to find the total number of workers are different. W equation and W star is going to be differently found. So W star is going to be an integer which has to be greater. You have to just round it up to the next level, sorry, the next value for whatever answer you get for TWC by TC, and W, only W, that is workload upon a available time. So when we solve the problems, this difference will be understood clearly. So as of now, just write down clearly that it is W star, that is minimum integer which should be greater than or equal to TW by TC. So if we assume one worker per station, then M subscript I value will be 1, for I is equals to 1, 2, and so on. So the number of utility workers will be 0 because the manning level is given as 1. That means only there is one worker working at station. WU, that is utility workers, are 0 at that station. So in this ratio also gives the theoretical minimum number of workstations on the plant. So achieving this minimum theoretical value in practice is very unlikely. So above equation that you see, it ignores two critical factors that exist in a real assembly line and tend to increase the number of workers above the theoretical minimum. So as we said that this equation basically ignores the two critical factors, and those are repositioning losses. Repositioning losses means what? Sometimes sometime it will be lost at each station for repositioning of the work units on the or the worker. So this time is available for worker to perform assembly. um, to perform assembly is less than TC. So repositioning losses is the time basically lost in either repositioning the work part or maybe the worker. So when it comes to this minimum integer equation, that is W star equation that is there, it does not consider these issues or these critical factors. One is repositioning losses and the other one is the line balancing problem. So in the unit ahead, we are going to discuss about these repositioning losses, how they can affect and how they can be taken care of, as well as the line balancing problem. What do we mean by the line balancing problem? It is virtually impossible to divide the work content time evenly amongst all workstations. Yes, we agree with that. But some stations are bound to have an amount of work that requires less time than TC. So this tends in increasing the number of workers. Okay, so line balancing problem is what basically we are trying to achieve an equal distribution of work and time at every station, but that practically does not become possible. Therefore, now comes into picture these different methods that we have: the largest candidate rule, the Kilbridge investor method, which is basically going to help us achieve this line balancing, or do away or solve this line balancing problem on these manual assembly lines. So repositioning losses, we'll take it in the next class, um, or we'll just finish that and then stop. Okay, line balancing problem, I'll start from the next class because it has problems also in it. So as I said, this is one of the critical factor that needs to be considered whenever you find the minimum number of workers required. So repositioning losses, they occur on a production line because some time is required each cycle to reposition the worker or the work unit, or at times it is even both of them. For example, if you consider a continuous transport line with work units attached to the conveyor and which are moving at a constant speed. Okay, I repeat, suppose if we consider a continuous transport line which has work units attached on the conveyor and are moving at a constant speed. So the time required for the worker to walk from the unit just completed to the upstream unit entering the station. Um, in other conveyorized systems, time is required to move the work units from conveyor and position it at the station for the worker to perform the task on it. So in all manual assembly line, what happens? There is some time which will be lost in all these repositioning. So let us define the repositioning time as TR. So we have already even come across this. Mm, yes. So repositioning time, that is the time available each cycle for the worker to position, is given by TR. So the repositioning time TR, it must be subtracted from the cycle time to obtain the actual available time remaining to perform the actual task on the workstation. That is nothing but the service time. Okay. So service time, it is symbolized by TSI, T subscript SI, where I will, which is nothing, it just identifies the station. So service time will vary amongst all the station because work or the total work content, it cannot be allocated evenly amongst all the stations. So some stations will have more work than the other station. So there will be at least one station at which the TSI, that is service time, is going to be maximum. So that station we call as the bottleneck station. So that is referred as the bottleneck station, which basically will establish the cycle time for the entire line. So we have already known this concept of bottleneck station and how it affects the cycle time. So bottleneck station, whatever time it takes, that is the maximum time taken by any of the station, will be taken into consideration while calculating the cycle time. So this maximum service time, it must be not greater than the difference between TC and TR. That is service time, TS, it is given by TC minus TR. You can just write down this equation. Service time is given by TC minus TR. It is max of TSI less than or equal to TC minus TR, where TSI is service time for station I, where I is equals to 1, 2, and so on up to N. So repositioning losses, they reduce the amount of time that can be devoted to productive assembly work on the line, because out of the available time, there is some time that is getting wasted in repositioning all the work elements. Either the worker or the work element needs to be repositioned. So because of these repositioning losses, the total amount of time that can be actually devoted for the productive assembly work will be reduced. So these losses can be expressed in terms of an efficiency factor, and that is given by ER, that is repositioning efficiency. It is given by TS by TC. We know TS is TC minus TR on TC. So this is the equation for repositioning efficiency. So there are certain components of cycle time at several stations on the manual assembly line. So we are talking about cycle time, there is repositioning loss, there is this actual service time. So we'll just see that with the help of this figure. You can see on the y-axis we have cycle time TC, and on the x-axis we have the we have the number of stations. So here we have TSI, that is the service time, and TR, that is repositioning time. So if you can see this figure that is shown on this slide here, this represents the components of cycle time at several stations on manual assembly line. So at the slowest station, the bottleneck station that is there, the ideal time will be 0, and at other stations, ideal time exists. So here basically these, if you can see this, this is the bottleneck station that you see, which does not have any ideal time. So this basically decides the cycle time. This, if you consider at station 1, there is this green box or this green line that is where it ends. This much time is basically spent in repositioning, and then this brown color part that you see, that is the actual service time. But then there has to be some ideal time, because the cycle time is decided by this bottleneck station. This bottleneck station, if you see, it will not have any ideal time. Okay, but this is the slowest station that is there. So based on that, all other, at every other station, the cycle time is going to be decided. So if you can see, this is station 1, 2, 3, 4, and so on, station n stations we have. So the ideal time here is associated with those stations which are not the bottleneck stations, which are not deciding the pace of the assembly line, right? So this basically tells you what are the components of cycle time. If you can see cycle time, this complete area here, this represents the cycle time. It is made up of repositioning time, the actual service time, and ideal time in case of a non-bottleneck station. Whereas if you consider a bottleneck station, it will not have any ideal cycle. So I hope these things are understood. In the next class, we will start with the line balancing problem, and we will start solving the problems of this unit. So we'll stop here today, and we will continue in the next.